Hello, and welcome back to the Chemistry Lecture Series. This is Topic 2, Video 4, the atom. In this lecture, we will be discussing the atom, its basic properties, the particles that make it up, and that's really about it. We will be looking at the atom more closely as we go along, but this lecture in and of itself is only about the basic information about the atom. So let's get started. This is an atom. Well, it's not actually an atom. It's a model of an atom. And what you're looking at is the Bohr model. This is the most common version of the atom we will look at, and it's probably the most useful for this level of content. In this model, you have the nucleus, which is usually represented by a ball of mass in the middle of the atom, and electrons. And these electrons are located in different places around the nucleus based on their energy level. This will be discussed very in depth when we talk about electrons themselves. The first part of the atom we're going to discuss is the proton. Now, protons are located in the nucleus. Remember the big blue ball in the middle of the atom we just looked at. Protons are positive protons. Should be easy to remember because protons and positive both start with the letter P. Protons have a mass of 1 Dalton. Now, an atom's mass basically comes from the things in the nucleus. The electrons don't really contribute to the mass, and it's really small, the mass of an atom. Each atom has its own unique mass based on the particles that are present, and the proton is one of the particles that contributes to the mass of the atom. We say it has 1 Dalton because the actual weight of a proton is 1.67 times 10 to the negative 27 kilograms. Now, if you take the time to write that out, in fact, why not? We've got time. Let's go ahead and write that out. Let's see. That would be 0. Oh, I'm writing in black ink. Can't do that. There we go. 0.00000000000000000000167. Now, that is a ridiculously small number. So it's much easier to represent the mass of a proton as 1 Dalton because, let's face it, 1.67 times 10 to the negative 27th is just a hard number to work with. We will work with it later, but not right now. In modern physics, just as a fun fact, the proton is actually not as small as it can be. It can actually be broken down into 3 quarks, 2 up and a down quark. But if that information interests you, you should be taking a course in particle physics, not chemistry. So why are protons important? Well, protons not only contribute to the mass, but they determine the properties of the atom. The number of protons present tells you which atom is present. The number of protons present tells you what particles will be, what properties will be present. The protons tell you the atomic number. In fact, if you look at your periodic table, the whole number represented on your periodic table is the atomic number, and that's the number of protons present in that atom. For example, the atomic number of hydrogen is 1. That tells you that hydrogen, each atom of hydrogen has 1 proton. The atomic number of, let's say oxygen. Oxygen's atomic number is 8. That means every atom of oxygen has 8 protons. If the atom has more than 8 protons, it is no longer oxygen. For example, if you add a proton, it's not oxygen anymore, it's fluorine. Fluorine will kill you, oxygen's good for you. So 1 proton at the atomic level means a world of difference to us as human beings. Neutrons are the other subatomic particle that contributes to the mass of the atom. Neutrons influence not the chemical properties of the atom, but the radioactive properties of the atom. Neutrons have zero charge. That means they are not electrically active. They are neutral. Just like protons, they have a mass of 1 Dalton. So every particle in the nucleus of an atom has a mass of 1 Dalton, or 1 atomic mass unit. In modern physics, the only difference between neutrons and protons is the type of third quark. Both have an up and a down, but protons have 2 up and 1 down. Neutrons have 1 up and 2 down. So, a little fun particle physics fact for you. Why are neutrons important? Well, number one, they contribute to the mass of an atom. And the mass of the atoms is very important to us, especially when we get to stoichiometry. Neutrons also determine which isotope of an atom is present, and while isotopes have the same chemical properties, they have different radioactive properties. Carbon-14 is slightly radioactive. Carbon-12 is less radioactive. They're both carbon. They both are coal brown. They both are very inert. They both form 4 covalent bonds, but those 2 extra neutrons in carbon-14 make it a different isotope. Neutrons contribute to the mass number and the atomic mass of an element. Now, there is a difference between the mass number and the atomic mass of the element. The mass number is the total number of particles in the nucleus of a given atom. Now, that's just one atom. If you're talking about one atom, it has a mass number. For example, carbon-12, it has a mass of 12. Carbon-12 has a mass of 12 Daltons. It has an atomic number of 6. That means it's got 6 protons, and if its mass is 12 and it has 6 protons, that means you've got to have 6 neutrons. The atomic mass is a slightly different term. The atomic mass is the average mass number of all atoms that we know of here on Earth. Now, there's not scientists out there who go out and count atoms. That's impossible. We just take the relative abundance, what we think the abundance of those isotopes are, and we average them, and we come up with the atomic mass of an element. For example, chlorine's an easy one because chlorine has 2 isotopes, chlorine-35 and chlorine-37. They're both found in nature. They're both chlorine. They both possess the same chemical properties. But there is more chlorine-35 than there is chlorine-37, which means when you're dealing with chlorine in the lab, you're probably dealing with chlorine-35. There's no real way of knowing, but for the most part, we know chlorine-35 is what we're dealing with. Because there's more of it, the average mass number is 35.45. That's our atomic mass. That number, 35.45, oh, I don't have my, there we go, 35.45 is closer to 35 than it is to 37. That tells us that chlorine-35 is more abundant. Now what you're looking at is, well, my drawing of what a periodic table should look like, at least the boxes within a periodic table. Not all periodic tables are the same. They're not. Every publisher does it differently, but they all have at least 3 things in common. Number one, they all have the atomic number. The atomic number is always the smaller of the 2 numbers. It's not always located in the same place. Sometimes the atomic number is up here on the top, in the middle, sometimes it's to the right. It doesn't matter. Whichever number is the smaller of the 2 is your atomic number. You also have the atomic mass, and different periodic tables represent that to a different number of significant figures. This one's only representing it to the first 2 digits. The actual atomic number, the atomic mass of carbon is a very different number. It's actually 12.011, and then it goes on and on from there. But different periodic tables will represent it out to a different significant figure, but it's always the larger number is the atomic mass. Notice 12 is larger than 6. You know that's the mass because the mass typically is larger than the atomic number. Well, it's either larger or the same. It can't be lower than the atomic number. You've always got the chemical symbol. The chemical symbol is the big thing in the middle. That doesn't change. And then sometimes the publisher will give you a symbol over here. And that is the state of the matter at room temperature, or standard temperature and pressure. A box is typically representative of a solid. A teardrop is representative of a liquid, and gases are either, there's a variety of symbols, but sometimes it's a cloud, sometimes it's something different. But not all periodic tables have that, but a lot of them do. Electrons are the last subatomic particle found in atoms. Electrons are located around the nucleus in probability clouds called orbitals. Electrons are negative. They are electrically negative, whereas the nucleus is electrically positive, and in nature, opposites attract. That's why the electrons fly around the nucleus. Electrons have a mass that is almost 1/2000th of that of a proton. It's so small that it translates to nothing when you add the mass of the electrons to the mass of the atom. That's why we call it 0 Daltons. The mass of an electron is actually 9.109 times 10 to the negative 31st kilograms. That's even smaller than the proton on a, like I said, a magnitude of about 1 out of 1800. And if you ever played with a calculator, if you add a really small number to a really big number, even though they're both really small numbers, the proton's number is so much larger that if you add the mass of the proton, it makes almost no difference. In modern physics, unlike protons and neutrons, electrons are an elementary particle. They can't be broken down any farther. They are as small as they possibly can be. In chemistry, we are concerned with electrons. Electrons are what we study, basically because electrons determine the bonding and the chemical properties of the atom. Electrons are the balancing force with the protons, so the protons and the electrons kind of determine what the atom does. That's where we're going with this, is how electrons behave to form chemical bonds. First and foremost, the differences in the number of electrons and protons determine the charge of an atom. Protons are positive, electrons are negative. If you have more electrons than protons, it's negative. If you have more protons than electrons, it's positive. It's simple math. Additionally, neutrons have zero influence over the charge of the atom. Neutrons are basically negligible when it comes to bonding. The charge of the atom has an influence on the chemical behavior. If you've got an atom that's a +3 charge versus an atom that's a +1 charge, that +3 charge atom will be more reactive because it can bond with more things. If you've got an atom that is -4 versus -1, the -4 molecule will probably be more reactive. If atoms lose electrons and become positive atoms are called cations, which is basically cations. The definition is a positively charged ion. An ion is a charged atom. Atoms which gain electrons are known as anions or anions. I don't know which term you've heard, but it's the same thing. An anion is a negatively charged ion, which is a negatively charged atom. So, two atoms are at war. One asked the other, "Have you lost an electron?" And the other atom says, "Yes, I'm positive." We'll see you next time.